We are going, well, it is hunting season, so it is my pleasure, or it's going to be hunting season soon, it's my pleasure to introduce Andrew Burkhardt, who is going to take us on the hunt for lost interstellar rings and chains. Take the stage.
All right, thank you. That makes it sound a lot more exciting. When I hunt, I was always envisioning this of like someone on the metal with a metal detector on the beach, just aimlessly wandering, trying to find these, you know. Yeah, so thanks for letting me give this talk today. Obviously, a lot of the talk, the stuff I'll be presenting here, I didn't do myself, as evidenced by the large contingency here in Green Bank today. Obviously, this is a large and really great collaboration here. I've highlighted some of the people's work I'll highlight are here in green, and everyone who I believe is actually physically here, I've highlighted in yellow. If you're both, I've got you both. Brett, you're just all yellow, you're just here. In general, so this is our collaboration, and it's really great, as kind of Brett highlighted. It's got a lot of you know, young career people, and I think it's a really nice spread of kind of a good demonstration of kind of incorporating all the different aspects of AstroChem into one big project where we have good modeling efforts, good observation efforts, good laboratory efforts, you know, both on the chemical modeling side and kind of the machine learning work. So I always kind of like where you get to dabble in everything that you want to do. And thankfully, when I go to talk about Gotham, Brett already had a really nice talk earlier this week, so I think I'm going to go through it a little bit faster than maybe he did, kind of as an introduction. This is a little bit out of date, only 2021, but you know, this is kind of similar to what Brett was showing of all the interstellar molecules that we know about and have detected. And I'm going to mainly highlight here this kind of end tail of them of this kind of new regime of chemistry that's recently been detected as of 2018, mostly due in part due to the Green Bank telescope. And that is primarily due to what we've been kind of been hinting at for a while here of interstellar aromaticity and aromatic molecules. These molecules are known to be very abundant, widespread throughout the interstellar medium. Here's a nice paper here with some Spitzer observations of pH emission from a wide variety of sources, from PDRs, planetary nebula, T-Tauri disks, Seyfert galaxies. Basically, everywhere you look, you see these observational evidence of these polycyclic aromatic hydrocarbons. And even more exciting, with the launch of the James Webb Space Telescope, we are now actually detecting, you know, pH signatures with the James Webb Space Telescope. For those that didn't see, there was a recent press release of PDR early release science, which had this really beautiful image here. And the fact that we're actually, you know, one of the key goals of that project is to look at pH emission in this exquisite kind of much higher resolution and sensitivity than we really had up in the infrared at this wavelength. But why do we actually care about these molecules? Well, as we kind of hinted at, one big reason is these molecules, when you get these kind of multi-ring species, they kind of tend to lock together, and eventually they'll form things like interstellar dust, which then end up forming the basis for both the majority of the chemistry that we know about. Are kind of it's required to have some form of interstellar dust. They form the building blocks of things like planets and many of the solar system objects that we have. They're key temperature regulators in a lot of, and you know, a key source of infrared emission throughout the universe, as I mentioned. And so, kind of any project you work on, it's one way or another, you're probably going to be working with pHs in one way or the other. And so we recently have been working on this Gotham project and the kind of partner project Arkham of these. Gotham project was somewhere between 900 and 1,000 hours, looking just towards TMC1 over a wide range of frequencies, kind of utilizing the really great sensitivity capabilities and spectral capabilities of the Green Bank telescope, integrating down really deep to detect new molecules towards the first source that we found, an aromatic molecule, benzonitrile, towards the source TMC1. And the partner project as well, which was not quite as large, but still a substantial effort here, was Arkham. Of course, we got to have our two partner names have the same theme. So this was our rigorous K-band hunt for aromatic molecules, where we're searching for benzonitrile outside of TMC1, right? So we know that it's here. We know that chemical complexity reaches very high degrees of, you know, multi-ring species, but we want to make sure that TMC1 is just not a unicorn of, you know, aromatic richness. And what's really exciting with our first data release of Arkham was in the first 5 sources that we looked at, including TMC1, we discovered it in all 5 of them. And this spanned a range of kind of from kind of young to old sources that are all within this kind of early stages of star formation. From a very young cloud, the 3 of these were in the Serpens cloud that was originally identified by high HC7N emission during Rachel Friesen's ammonia surveys. And and then even goes down to these kind of older sources where the protostar is just starting to turn on. And so we actually found that aromatic chemistry is ubiquitous throughout the earliest stages of star formation. So, that means that if we expect to see aromatic chemistry here in TMC1, we can maybe extrapolate out what we learned scientifically from there out to kind of more, more broadly to kind of early star formation in general. And so this is kind of our first big result from ARCM, and obviously, as people maybe have heard, there's the Gotham project has been widely successful at detecting new molecules, including Maddie Sita, an undergrad at UVA, recently an undergrad at UVA, with this recently announced detection of cyanoindene. We have a wide slew of kind of a rogues gallery of different molecules that we've been able to detect, and a lot of them are these kind of cyclic molecules, 5-membered rings, 6-membered rings, or some combination thereof. And in addition to large carbon chains that I'll kind of highlight a little bit later in the talk as well. And so what I'm going to focus on a little bit here is understanding, okay, now that we know they're here and we can tell that they have a certain degree of abundance, that we can detect them pretty readily, albeit with a lot of work, we now kind of have built up in a way of a large number of these different species. So we know they're there. So now the big question is, how the heck did they get there, right? How do we form these types of molecules, right? So we kind of took our first stab at trying to model these, how we typically model a lot of molecules in sources like TMC1. You run a chemical network model. The one of our choice is Nautilus. So basically what this does is it solves a system of tens of thousands of chemical reactions, solving a large ordinary differential system of ordinary differential equations. And you end up getting the abundance of these molecules as a function of time, starting with the initial elemental abundances and then building up. When you get to about the age of something like TMC1, you'll get these peak abundances of these certain molecules. Now on this plot here, I have kind of among Gotham the kind of different types of rings that we've detected, where we have the 5-membered ring here, cyclopentadiene, we have benzene, we have indene and naphthalene. And so among these 4 different types of rings, you have the pure, we'll call it kind of pure hydrocarbon version. So this would be no CN added to it. And those are shown in the orange lines here. And the blue lines here are the cyano versions of it. For example, benzonitrile, which is just benzene with a CN attached to it, would be this blue line here, associated with the benzene, which is this orange line here. And also guide your eye, the gas phase abundance in the molecules is the solid line, and the solid phase, aka what's kind of frozen in the ice on dust grains, is the dotted lines here. And the kind of big takeaway is that these horizontal bars that you see at the top of these plots are what we observe with the Gotham project, and the models are all way too low. We have this abundance of riches. We're seeing way more than we possibly see. And so for context, this one gets a little close, but you have to remember that this is benzene, but what we're actually observing here is the blue line, so that's benzonitrile. So we're actually a couple orders of magnitude below what we expect. And that's for benzene, which is like that, benzonitrile is the first one we modeled, the first one we observed. And basically everything else is several orders of magnitude worse than that, right? So clearly we're seeing way more of these molecules than we expected, which is great because it means there's a lot of chemistry here that we don't understand. But now we have the hard job of trying to figure out, okay, how the heck did it get there? So in terms of the origin of aromatic molecules, there's kind of a top-down versus bottom-up kind of scenario that has been kind of debated using these models where we start with initial elemental abundances and then you build up molecules. This is what we refer to as bottom-up. So what potentially could be explaining what's going on here, why we're not producing enough, is just that our models are not complete. And that is a personally reasonable explanation, given that our first stab of it is probably not 100% correct because we've never really had to model these molecules we've been modeling carbon chain molecules since, Eric Herbst first wrote them, several decades ago, but we haven't been able to really, study PAH formation or even one single ring up until probably 10 years ago. And so there's just a lack of knowledge within these networks. Some of these other ones I'm going to quickly kind of go through about our kind of thoughts on them are the kind of more top-down formation routes of these molecules. So, for example, one may just say, okay, well, we think that, maybe when you heard initially in one of your astronomy classes that we think that you have these, dust formation occurs in evolved stars. You have these, rich carbon or silicon atmospheres, and you form either silicate-based dust or carbonaceous-based dust, depending on whether you have a carbon-based or oxygen rich evolved star, and then you form these kind of rings, and then eventually those will survive into dust and everything we see today. So that was kind of the story, at least I always feel like I heard initially. And so the thought could be, okay, well, maybe these just rings were here before, when we go to look at TMC1, we were simulating it from the ground up. Maybe the molecules were already there, right? They were formed during the evolved star phase, and they just stuck around. So to test this, what we did is we took our chemical model. We just took the exact same chemical model that we've been using, and we just started out, instead of just saying, we're going to start with a bunch of carbon, and we're going to build up. We just started out with, in this model here, 10 to the 5, an abundance of 10 to the 5 of benzene, which basically means we're putting almost the entire carbon reservoir initially just into benzene. So what you're saying is almost every single atom of carbon is there. And you have to get to about that abundance to reproduce the gas phase abundances of benzonitrile that we see. And the reason why is because these molecules are rapidly destroyed through the large amounts of elemental carbon and other kind of atomic ions can rapidly destroy them as you're kind of building up the rest of the chemical complexity in the network. And so, and this is kind of also aligns with what we kind of think more generally is that in diffuse clouds, either kind of ion neutral reactions or high UV photons destroy many of these smallest rings. And so it's kind of our belief, although it still warrants a lot more study, that we don't think necessarily that these small rings are inherently inherited from the from the evolved stage. Another way that you could potentially think about it is, okay, well, maybe only the really big rings survive, right? They're a little bit more stable to UV photons. They can dissipate their energy out a little bit more. And so maybe you have, these really big rings are formed in the evolved stars, and then the small ones are destroyed when you go through the diffuse cloud stage. And maybe once you start getting into these kind of dark cloud areas again, maybe for whatever reason, you're able to break apart these either more mechanically or maybe chemically or with some sort of photodissociation process. That is going to require a lot of incorporation and assumptions about how these PAHs are destroyed, and could even be a source, another potential source of these PAHs could just be the fact that the dust grains themselves, carbonaceous dust grains, are actually just made of PAHs. That's currently not within our scope, but it certainly could actually be the answer. But I think in terms of right now, it's a problem that's probably several PhDs worth of work. So I think, I think it's interesting. We're not going to be following that train of thought, at least for now. We're going to go back to bottom up and try to see, okay, let's throw the kitchen sink at this. Let's try to build out our network as best as we possibly can with what we know about, and try to see if we can reproduce the abundances this way. All right. And so I mentioned also that benzene and benzonitrile kind of get pretty close, but and so we're going to focus mainly on those because we think that if we can get benzene right, it's going to help increase the abundance of all the other rings, right? Because we think that it's kind of your base ring that you start with, and you can kind of click together all the other ones once you get it.
Is this only in TMC1 right now?
Yeah, this is just TMC1.
Right. So you have not done this for any other sources?
These models. I did modeling work for the Arkham in the original Arkham paper and stuff. That's where you get to, we need to know the physical conditions of those sources a little bit better. And for a lot of the sources, some we know, some we don't. But we haven't done detailed physical modeling of those quite yet. Right, and so first we're going to focus on benzene and benzonitrile. And one of the reasons why we really think that this is kind of a worthwhile, benzonitrile in particular, is because Ilse Cook will be here actually in a day or two. maybe today, I don't remember when actually it's coming. It's really, really nice lab work to show that the reaction of benzene plus CN going to benzonitrile is both efficient and extremely consistent over a wide range of temperatures. And so we believe that this type of reaction should be efficient for most aromatic molecules, that if you just have some aromatic, some purely hydrocarbon version of a ring, adding CN is a fairly trivial matter. Brett, I know, went into a lot of detail about the specific attack of it. So right now, I'm going to go with the assumption of we're going to try to get as much benzene there, and we're just going to assume that benzonitrile and this other molecules are going to follow, right? And so similarly, right from Medicida's paper, we believe that this CN plus some ring, some cyclic species, should be kind of a translatable relationship as we go up, right? So what are some of the ways that we're going to try to throw the kitchen sink, right? So one of the ways is we can try to make a more robust network of basically the precursors to these rings, right? So I kind of envision this chemical model almost as like a giant pyramid, where the top of the pyramid is you have a few reactions that are able to make benzene. And at the bottom, we have all the work that we've been doing for decades to build up these small carbon chain molecules and clip them together in every which way. And this would be the perfect picture, right? So you start with carbon and some hydrogens, and then you get some C2H2, and as you get larger and larger carbon chains. But unfortunately, if I were to actually make a picture of how I view the model, this pyramid, it's kind of missing most of the center bricks. It's held up by stilts that are probably just estimates by PhDs who are trying to get a paper out really quick, and then no one bothered to update it. And so this is what I've been working with Anna Appalato, who's an undergrad at Wellesley College, on incorporating and kind of building out a more robust semi-saturated network, a network of semi-saturated carbon chains. So these are molecules that have 3 to 6 carbons and different degrees of how many hydrogens, somewhere between like 1 and 6 hydrogens associated with them, to try to see if we can build up that transition from these small carbon chains that we really feel like we understand well in these sources up to these larger cyclic molecules like C6H6. And so we're incorporating some of the work here by Loisan et al. In 2017, but a variety of other kind of sources of laboratory work. A lot of it doesn't necessarily exist though, so it's going to take a lot of kind of hard work, including some of the great work by some people in this room here as well, by Alex and Cece over at MIT. And they've also been doing, in addition to adding in some very similar networks and reactions that we've been doing, they've also had a lot of really interesting results of, for example, looking at the branching ratios of different reactions. So we always just kind of naively assume, if we don't have any better idea, if you have a reaction and we think there are 2 pathways independent of any other information, we may just say, we don't have enough laboratory data, we're going to assume 50% go into one set of products and 50% go in the other. It's probably wrong, but it's the best we got, right? But after doing a little bit of detailed work in the literature and doing some extra calculations, they found that one of the most important precursors, specifically looking at the formation and the destruction of C6H7 plus and C6H5 plus, which we think are some of the primary precursors, that we actually got the branching ratios a little off to the detriment of forming benzene, to the point where if we corrected them, we should actually get an actual decent increase in abundance. So this is an updated version of the model of these bottom 2 are benzonitrile and the top 2 are benzene. And the dotted lines or the dashed lines are the old version of the model before we kind of incorporated a bunch of this new information. You can see we get about an order of magnitude bump in benzonitrile and an order of magnitude bump in benzene. And we're still roughly an order of magnitude out. But if you go talk to chemical modelers and you say, yeah, you know what, we got that to within order of magnitude, pack it up. We're getting there. We're getting pretty close to home. I'm not going to say it's perfect, and obviously we need to increase the abundance more to be able to explain a lot of those larger rings, but we can show that this is a technique that's clearly working, and increasing the abundance is these kind of dedicated efforts of filling out the pyramid in a way. Another avenue that our group is looking into is looking at, do these rings potentially form on dust grains through various methods, either through radiation chemistry, maybe through the erosion of dust itself, I kind of hinted at. Or just, you take a carbon chain, you place it on the dust, you have a bunch of hydrogens sitting around in the ice as well. You can add a bunch of hydrogens and somehow you get it off. And so a lot of people are working on this in the group. Tanya Lambert's over in Leiden, Chris Schinkelbecker over at Benedict College, and Alex Paulov over at the University of Virginia. I've been all kind of working on this, tackling this problem. And another kind of avenue I don't really have time to get into, but another way we can start tackling this that Gotham is really going to give us some information on is looking at the isotopic composition of various kind of precursor molecules. And by I had this paper in 2018 kind of that went alongside the benzonitrile detection then, which showed that we think we can constrain potentially the dominant production routes of some of the larger cyanide polyions by figuring out the relative enhancements of different isotope positions of 13 carbon within the molecule. So here we're able to find that HC3N is kind of believed to be formed primarily with CN as a primary precursor due to the relative enhancement of that position, but we didn't see that enhancement necessarily for HC5N and HC7N. And so we have a lot of isotopic information in Gotham that's just waiting to get cracked open. And so this will be an interesting avenue to do a really dedicated study of all the relative isotopes and how you trace them throughout and where those enhancements are coming in. And this is, instead of just kind of guesswork of let's try to match the abundances, it's a very strict and kind of programmatic way of are we actually producing it? Yeah. And so kind of the last little thing here I want to talk about is K-band going forward. You know, how is K-band, what's K-band's role in our search for understanding aromatic molecules, right? Well, first of all, as you know, the new molecules are always very exciting. The really big ones, you know, they're the kind of flashy ones. But in these models particularly, right, for us to understand, every single species counts, right? So this is one that Chris Shingledecker worked on. You know, it doesn't look too flashy. It's a cool carbon chain. It's got 3 hydrogens on it. But this semi-saturated carbon chain, when he started doing the model, he realized he actually needed a grain formation route. That was the most efficient way to produce a molecule. While the vast majority of the chemistry we do in TMC1 is primarily gas phase. And so this was some extra insight we only gained by looking at this specific molecule that we wouldn't have gone to look at. We wouldn't have written a proposal to go look for this molecule, but because we had this sensitive wideband survey, we were able to look for this type, study this type of molecule, right? And Gotham and Quixote's surveys are both dominated by these carbon chain molecules. This is the workhorse of what's actually being detected in these. And K-band, as we kind of talked about, is a great sweet spot for looking at these types of species. Both detections and non-detections are important, right? So what's great about these blind surveys is even if you don't detect anything, we still get a lot of science for these models, right? This was a really, really nice paper that Tim Barnum and Elsa Cook worked on, where they took predictions. So all these little dots are using kind of UMAP, kind of language neural networks, using stuff that's way more complicated than I can explain very quickly or understand. You know, each of these dots basically says a different molecule we found in TMC1, and then by understanding the chemical properties of it, we can predict what other molecules we think should be in TMC1 as well. So we took kind of our best guesses from that approach, and then we just stacked those molecules and tried to see if we can find them. And one family of molecules we studied in that particular paper was this family of heterocycles, which are rings instead of being kind of pure rings with something kind of attached onto the end like a keychain. Instead, there's things that are actually locked into the actual ring, right? So here's an example of one where you know, not every single element in the ring is necessarily carbon, and we tried to find some upper limits to these molecules, right? And this is really important because for the chemical models, all our upper limits, you know, are typically done just by people detecting abundances. But by having any upper limit on some of these other species, they allow us to constrain pathways for these molecules. And so these are only possible with kind of these sensitive wideband surveys, because again, we can go and try to hunt for each one of these individually, but it's just more efficient to do it all at once, right? Because we often don't even know what we're looking for until we get there. And finally, I want to hit a little bit on Arkham. So this is a quick kind of representation of some of the spectrum we're seeing from a bunch of our Arkham sources from 22 to 31 gigahertz, where we did dedicated studies to look in the K-band and up here some stuff in the Ka. And basically what we found is if you want to find benzonitrile, if you want to find these rings, K-band is the place to look. It's the, you know, as kind of Brett mentioned, it's the sweet spot for frequency coverage. We can look pretty easily for benzonitrile and a couple of the other species we think might be chemically related, or at least indicators of rich carbon chemistry. And by studying a wide variety of different sources, this will be vital for probing evolution over time, physical conditions. We can look at, okay, if we think they're destroyed by UV photons, we should see different amounts of aromatic molecules in areas with high UV photons versus low UV photons. There should be a difference there. And so we can actually start probing out parameter space of it instead of focusing just on one source in particular. And having wide bandwidth surveys not saying they have to be as wide as Gotham, but even just something having that bandwidth and frequency coverage, being as an efficient route, is what allows us to do this kind of science. And I think going forward, that's going to be a lot of what we're going to be working on. There's going to be diminishing returns on how much we can integrate on. I'd love to integrate on TNC1 forever, but there's other sources out there that are also really interesting, and we should also try to, take a stab at those as well. And so to, wrap up here, it's always onward and upward. Gotham DR4 is a fantastic set of with some really nice, in addition to new data, the calibration was significantly improved by Maddie Sita, who did a lot of really hard work. And so I think there's a lot of really cool detections that are still to come in here. Arkham, I think we're really starting to, long term, we're probably going to be shifting our analysis, a lot of it to Arkham, because as we start branching out into a variety of sources, doing the physical modeling that, Tony was saying that we need to do, and I know we need to do. And, I think it's only the beginning. A lot of the hard work now is expanding out and, the theoretical and laboratory work that needs to be done that's been motivated by these initial detections that we were able to find. Yeah.
Other questions? Comments? In the room, on Zoom? Yes.
Okay, question. So when is the data release?
Sorry, what was the?
When is the data release for?
When is the data release for?
Yeah.
So it doesn't actually stand for data release. It stands for data reduction. So we release the data when we have finished all of incorporating all of the observations for a single frequency setting, so that we're not versioning the data we put out publicly. So X-band is out, it's done. The K-band, KA, and KU that Andrew just presented, we just finished those a month ago. So those will probably come out, I'm guessing, this spring, as soon as we finish getting those incorporated.
But we heard about the White House's thing. As soon as they're published, they should be released right to the White House.
If people want the data, they're in the archive. I mean,
well, then that's not the same thing. That's not what the intention of that.
They can come get me. I'm not going to put out our intermediate data reductions when we're going to put an incremental, 10 more hours worth of observations in later.
Yeah, or we're doing minor flux calibration cleanup and stuff like that. So there's a lot of little things where it's,
yeah. But I'm telling you though, that's the White House said it, right? It's not
the White House can come sue me. Exactly. Yeah. If he wants it, he can get it on the CD from me.
So with Arkham, if you're looking at other sources, I'm assuming some of these sources might be slightly denser in like molecular concentration. Is that true?
Yeah, so in general, we're still keeping it primarily to kind of early stage star formation, so dark clouds or maybe very early kind of pre-stellar sources for the most part.
Okay, so then in that case, with aromaticity in these kinds of like multi-bonded systems, there might be like non-covalent interactions and stacking. Is that something that these models can account for?
Sorry, would you repeat that?
Oh, I'm interested in if the model accounts for things like non-covalent interactions, like that aromaticity can like affect.
It's currently not really. Yeah, if you the limitations of we're still building up a lot on the actual chemical network side and stuff, and so I think we're even just trying to get isomerization in there a little bit. That even that's preliminary for some of the different kind of aromatic species in here. So I think it's something we should do down the road, but it's work in progress. Yeah.
All right. Do we have more questions in the room on Zoom? Okay, then Pedro, go ahead.
Oh, I was just going to ask, are the data reduction tools publicly available?
Yeah. We have a whole paper where we go through it in detail, and when you actually go to like download the data, you can download the individual each individual data chunk that you use, including like these are the exact channels we use. This is the exact weighting we do. Theoretically, it should be completely reproducible. It's totally available.
And Sam can attest that our data reduction tools are available.
Yeah, I mean, Glucose is using the same infrastructure, also the same observing scripts. Thank you, Andrew. So everything has been easy and reproducible, and I'm the test case, I guess, for that.
If I can do my own thing. Also, the fact that we were able to do this remote, doing operator driven,
yes.
These papers would not be out if it wasn't operator driven. It would have taken, me personally, it would have taken a huge amount of work effort. So I am very appreciative as, the person who is kind of leading the charge on the observations. I'm extremely appreciative that we were able to do operator driven, it saved us a lot of headache. And I think it also kind of made everything a lot more consistent across, if things weren't working, we knew how they weren't working. So, having that capability for especially these large projects, I think is almost essential.
Questions on Zoom? Speak up if you have any. Raise your hand on the Zoom. We know you're there. Exactly. All right, if there are no more questions, there is we first thank the speaker. Oh, yes, sorry, you're my blind spot. Kind of.
Why haven't we targeted evolve stars?
Why haven't we? One of the easy ways I would say is they probably got a lot more broad lines, so stacking's a lot tougher. That'd be my first guess. Also, they're warm, so they're not going to be peaking necessarily in K-band as easily, right? Your bright benzonitrile lines are probably going to be shifted up to higher frequencies. So I think the combination of not being able to stack plus weaker lines, especially around, our workforce frequencies. That's it. We should do it, but we got a lot of stuff.
There exists in the literature a K-band survey of IRC 10 through 16 by the RT people or something, and there's no that's on it.
I think that's also like, is there a limit on this? I don't actually know what's the nitrogen abundance in RC 10 through 16.
I don't remember.
What you're presuming though is that you are building up in these dark clouds from the bottom up process, whereas I won't say general knowledge, but seeding of the interstellar medium by evolved stars, where you build up dust grains, build up large. You're saying that basically that is not a driver to putting this type of material into the interstellar medium. That basically it's destroyed too quickly.
At least
they are being formed in evolved stars.
Yeah, I mean, chances are it's probably a mix of both. It's probably not a holistic thing as of right now. At least the way I'm thinking about it is, if we throw the kitchen sink at it with the bottom up and we can get there, that seems like a nice explanation. If we throw a bunch of stuff at it and we're still not quite reproducing the abundances we expect, then we probably need to start thinking about top down.
Right. And with that, we have to stop the discussion now, move on to the next talk. Thank you very much, Andrew, for this.